So there's a few things in this, stuff that I meant to cover yesterday in some cases, or well, actually for a lot of this problem, stuff I meant to cover yesterday, and then just kind of skipped over it, but nothing we can't quickly recap on. So what we've got is this printout, and they're asking us to find the p-value for this t-test. And the good thing is we don't need to do any just one very minor calculation for this problem. We could do a more extreme calculation right here. Not when I say more extreme, I mean we could go through the full thing. It's going to be stat minus parameter divided by the standard error. And we've got those numbers right here. We don't care about the constant. So we can take our b and we can plug that in right here. We know this is going to be 0 because beta is going to be 0 for the null. And I can plug that in. We could calculate it out. And then we could do our degrees of freedom with a t-distribution, blah, 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 and figure out the p-value. Now, what I didn't show you yesterday and what I wanted to show you is that sometimes in these, it does that for you already. So after I calculate this, it's going to be 2.48. It actually gives me the t-value in the printout. And not only, it goes one step further and it gives me the p-value right there. So my p-value is given right here. And so you got this 0.0478, and it would be very tempting at this point to say, well, there's my answer, it's 0.0478. If you can read this printout, you understand that the probability is your p-value. And different printouts will have it shown slightly different ways, but you just kind of need to work through and understand that that's a p-value. It's easy to just say, oh, well, there's the answer, C. But this is where what we did talk about yesterday a little bit, we need to kind of think through. I mentioned, it was a small thing that I mentioned, but I did mention that p-values are always calculated with technology as a two-tailed test. So this right here is two-tailed. All right, that's not really showing up as a word that makes any sense, but that's two-tailed right there. If we look at our hypotheses and we specifically focus on the alternative, there's a typo right here. If we focus on the alternative hypothesis for this, what we will notice is that this is not a two-tailed test that we're doing. This is a one-tailed. We're only doing greater than. It would only be two-tailed if it was not equal to, but that's not what's happening. So because this is a one-tailed test, what I need to do is I need to take this p-value and divide it by 2. Because remember, you get your two-tailed test by multiplying your p-value by 2. So if I need to get back to a one-tailed, then I need to divide that by 2, and that will give me my final answer of 0.239. All right, so it's a tricky problem. In one sense, it's pretty straightforward because it gives us the p-value, and we're good to go. But in another sense, we need to kind of compare that to what our hypotheses are. And remember that we're always given a two-tailed, if I can think, two-tailed p-value, two-tailed test. So this is not the answer. 0.239 is the answer. So hopefully now seeing all that, it's clear enough. Not much to today. We did the bell work already, so we're just gonna get a bunch of practice. I pulled these questions from the AP Classroom. So they're not the same ones you saw in your progress checks. So if you did those or will be doing those, you'll see different questions, but a lot of them will relate very closely, you can imagine. So that's what we're going to be looking at today. A couple of FRQs that I'm not going to go in through and do both of them in detail, but whatever the case, we'll just go through that. If there are any problems that as we're going through them, maybe I don't explain it clearly enough for you, or whatever the case, you kind of zoned out, whatever, just keep track, and then we can come back and revisit any questions that you still have, any problems you didn't fully grasp. Some of these I'll skip. So let's just go ahead and get started. This was a pretty straightforward one. In fact, it's pretty much what our bell work was yesterday, but maybe it's worth seeing it one more time where, and some of these, I'm not necessarily going to read every problem, but just quickly glancing at this, you can tell that they give us an X value, they give us a re-expressed linear equation, linear regression line equation, and what we want to do is find the predicted value. So pretty straightforward. I'll plug in log of y hat equals 7.3 minus 1.5 times 4.8. So when I do that, you can quickly do that math as well. I get 0.1. And the way that we get y hat all on its own is by raising both of these values as powers of 10, right? So 10 to the 0.1, 10 to the log of y hat. These cancel each other out. So y hat equals 10 to the power of 0.1. And you can do that as a 10 raised to a power, or you could just do your 10x button and put in your 0.1. And you get 1.259, which matches up with this answer right here. Pretty straightforward. So hopefully no questions there, and you're feeling pretty confident with any question like that. Okay, a fitness center offers a 1-month program designed to reduce body fat through exercise. So anyways, we have the data from before and after. The director wants to investigate whether knowing the body fat percentage before beginning the program can help to predict body fat percent for someone who completes the program. Which of the following procedures is the most appropriate for such an investigation? Now, this is one that's a little bit, hopefully you have to think about it a little bit. You don't just automatically jump to an answer. And the reason I say hopefully you think about it a little bit is because you could be tricked by this problem. Because this is a classic case where a matched pairs t-test could be the right answer. It could be the right answer depending on the question they're asking. What if the question was, is this program effective? Then a matched pairs t-test is a great way of checking that. And we could do all this math. We could figure out the 0.1. We got 1.1. These differences right here, that's going to be, or that should be a negative 0.2 right there. So anyways, you could do a matched pairs t-test if it was asking, is this program effective? But what it's asking instead is, can we make a prediction of the after program body fat percentage? And so for that, we're thinking of a scatter plot where you have your before and you have your after. And of course, your body fat should go down, but still, if you started with a higher body fat, you're going to end with a higher body fat at the end. So it should look something like that. We're making a prediction. So at this point, it's going to be a linear regression t-test. Not that. So make sure that you're reading the problem, especially because right now, you know it's a linear regression test. So your brain is probably naturally going to think, oh, it's probably linear regression, just if I randomly guessed. And that would be fair for right now. But keep in mind, on the AP test, they're going to be mixing all these concepts together. So make sure you're reading through it carefully. Hopefully that's clear. All right, there are a bunch of problems like this in our display today, in our practice problems. So I'm not going to go through all of them, but we'll go through this one. And we want to create a confidence interval. In fact, just in general, I'm kind of like a lot of you probably are. I get lazy when it comes to reading problems. And I look at this, I see my printout right here, I see 95% confidence interval, and I kind of ignore the rest. So in this case, that wouldn't be a problem because it is asking exactly what you expect, but that's not a great habit to be in. There are probably times that has happened to you where you quickly thought what you knew the question was asking, you answered, and you didn't read it fully. Now in this case, it's asking for the 95% confidence interval here, so we're good to go. So when we look at this, remember this constant or intercept line we don't care about. We will look at it in one of the FRQs later, but just barely. So the rotation here is the representing the slope. And we've got two values here of interest to us. And so if we're thinking about our confidence interval equation, it's going to be stat plus or minus the critical value. Now write it out every time just because I want you guys to really get that to sink in. And hopefully by now you've got it memorized times the standard error. Now we already have the standard error given, so we don't need to worry about the equation specifically. It's going to be b plus or minus a t star value times the standard error. I'm not going to bother with the equation, though. For this one, it would be s over s of x times the square root of n minus 1. But we don't have these values right here, so we're going to skip it. Okay. So the standard error is given. I'm just going to substitute these two values in. Here's s, the SE, I can say, for standard error. And this is b right here. So it's going to be 0.04625 plus or minus t star times 0.01565. So just with that, you can rule out a couple of answer choices. And if you look at the remaining answer choices, the only thing that changes is the t star value. So that's what it comes down to. I'm not going to flip the screen over for you guys to see it, but if you can pull up your table B, you can find out the t star for this. So it's going to be a t 95% confidence interval, it says right here. And since there's 16, this is where you would have to go back and read the problem. Since there are 16 data points, my degrees of freedom is going to equal 16 minus 2, so 14. And I didn't check to see if this problem is set up to throw you off. So let's kind of look at this real quick. So for 14 degrees of freedom with a 95% confidence level, I get 2.145. And that means my answer is A. Now, if we had done this wrong and we had just done n minus 1 and gotten 15, then we would have been fooled into picking this one right here, because 2.131 is that critical value. So make sure that you're thinking through this correctly. All right, that's good with that problem. All right, another one that's basically asking the same thing. What's the 95% confidence interval? The difference with this one is that if you look at this, all the t stars are the same. So we don't need to refer back to that table. We already know it's going to be 2.086. That's not the question they're getting across. So they are, and almost all of the slopes are the same. So it really just comes down to where the difference is, because I can rule this one out. Which of these standard errors is correct? And luckily we know it's that value right there. So it's actually a really straightforward problem. All right, and you can get tricked into maybe selecting one of these because you know that this equation, s divided by s of x times square root of n minus 1, that might trick you a little bit, but not what we want to do. Actually, what they're doing is they're even referring this to s over square root of n. That's kind of how they're setting it up. So we know it's not that. And we don't need to worry about that equation. All right. I don't want to over-explain anything. So I'm going to keep moving forward. If any of this doesn't make sense, like I said at the beginning, just keep note of which problem it is, and we can come back and look at it later. All right, so here we've got meteorologists interested in the relationship between minimum pressure and maximum wind speed of hurricanes. So the minimum pressure and maximum wind speeds were collected for random sample 100 hurricanes in the year 95 to 2012. A regression analysis already produced a 95% confidence interval of negative 1.42 to negative 1.20, and we want to provide a correct interpretation. All right, so if they don't give me anything else to work with, of course, my only option is to read through the full problem. And just to emphasize good habits, read through the full question every single time. So before I get started, I always like to have some kind of a diagram showing what's going on. So it looks like we are using pressure to predict wind speed. And that would be kind of, maybe it requires some knowledge about the weather, but we would expect that pressure would predict wind speed, not the other way around. All right, so I will put minimum pressure right here, MP, and maximum wind speed, MWS, and it looks like they're getting a negative relationship between it. So I'll just draw this. I don't need to get more specific than that. But now what we can think about is knowing that this is a negative slope, it looks like as minimum pressure increases, maximum wind speed decreases. So minimum pressure goes up, maximum wind speed goes down. It's important to have that kind of conceptual understanding going into this. Now, if we were going to write this out as an interpretation for ourselves, then we have kind of our template that says, we are 95% confident that the interval from negative 1.42 to negative 1.20 captures the true slope, the true association or slope between minimum pressure and maximum wind speed. All right. So they're not going to have that exact answer. We want to see what makes the most sense. And remember that confidence intervals are saying that if we repeated lots of samples over and over, 95% of the time, we would expect the true population slope to be captured. So the probability is 0.95 that wind speed will decrease on average between, so it will either, this is saying that this is not a correct interpretation because there is a true value that exists somewhere out there. And it's not a 95% probability because it's either it does or it doesn't. What we're saying is that if we had a lot of confidence intervals, we would expect it to be captured 95% of the time. So anything like these two are basically saying the same thing. And I mean, this one slightly changes it a little bit, but that's still not the correct answer. So here's where we have some good looking answers. Okay, we are 95% confident that wind speed decreases on average between those values for each millibar increase in minimum pressure. So this is saying minimum pressure goes up, maximum wind speed goes down. So this one looks promising. The next one is almost the same, except it says maximum wind speed goes up as minimum pressure goes up, and we already know that's not the case. And then we can be 95% confident that for any sample of hurricanes, the wind speed will decrease on average between those values for each millibar increase, blah, blah, blah. Again, that's not the correct interpretation of this right here. 95% confident is kind of a shorthand for saying 95% of all of the possible confidence intervals will capture the true mean. All right, so the answer here is C. Sometimes these interpretations are the hardest questions. I'm going to skip this one because it doesn't really add any new understanding. So you can look through that one later. And this one too. I will go back really quick just to say, notice that this one, there we go. This one gives you your t-score and your p-value. So we don't need it for this problem, but you can see it can show up. And notice that this one's saying probability of greater than absolute value of t, and that's one way of calculating a p-value. All right. So we've got researchers believe that an increase in lean body mass is associated with an increase in maximal oxygen uptake. The scatter plot of the measurement taken from 18 randomly selected college athletes displayed a strong positive linear relationship between the two variables. A significance test for the null hypothesis that the slope of the regression line is 0 versus the alternative that the slope is greater than 0 yielded a p-value of 0.04, which is an appropriate conclusion for the test. So again, before I answer that, I want to have a visual. Lean body mass, LBM, is used to predict maximal oxygen uptake. And it says there's a strong positive linear relationship. So I'm just going to draw a line. As LBM increases, the maximal oxygen uptake increases. All right, so remember your p-value of 0.04 is just saying what's the probability of getting the results for the slope that we did if the null hypothesis is true. So the first two problems here, it says the p-value of 0.04 indicates that 4% of the variation, ... Well, the amount of variation is explained by r squared, okay? So that would be a good interpretation of an r squared value, but it's not correct for a p-value. A strong positive linear relationship displayed in the scatter plot along with a p-value less than 0.05 indicates that college athletes with higher lean body mass tend to have higher maximal oxygen uptake. All right, that one looks promising. I'm going to put a star next to it. The strong positive linear relationship displayed in the scatter plot along with a p-value less than 5 indicates that an increase in lean body mass causes an increase in maximal oxygen uptake for college athletes. Well, that's almost saying the same thing, and they both look pretty good. The next one says that the relationship is likely due to chance, no statistical evidence. Well, no, we know that it is statistically significant. So between these two, which one seems to be the better choice?
I think D, because it specifies that it's college athletes.
All right, well, it specifies it in a different spot here. Yeah, no, that was a good thought. That was a good thought. I'm glad that you kind of were looking for something like that, because that could have been the answer, or that could have been a reason for the answer. Any other thoughts on this? My phone has a thought. All right. Now, I know I'm kind of cutting into your thinking time. I do that a lot. I apologize. But hopefully you've read this a few times. And maybe it took me reading it a few times before I finally caught what was wrong with D. The correct answer is C. So just focus on D. Why would D not be correct?
It says it as if like body mass can just increase over the course of this test, and like I don't think that's the case, because like, you know, body mass is your body mass. You're like, you have that. So C like says that they already have the body mass, which causes the higher maximal oxygen uptake.
Well, you're onto something with your thought process, but that's not exactly it. I'll just say there's one word that causes a problem. Oh, go ahead.
Maybe because they say lean body mass causes an increase, but in reality, it's just like it comes with the other.
Yeah. Well, and we haven't set up an experiment. This isn't really something you could set up an experiment for. You can't randomly assign someone to have lean body mass of this amount and someone to not, you know. So an observation, but we cannot make a causal conclusion. We cannot conclude anything causally here. So that's the problem with part D. Okay, and it's a very subtle thing, because you could read both of these over and over again and just forget that one little bit. So glad that we see this question, we can look at it. Okay, this one, pretty straightforward. We had 21 roller coasters, maximum speed and maximum height were put into an association, and basically we got this residual plot. And they're saying right here that we cannot do the, or the conditions haven't been met. So which condition does it appear we did not meet? Do we see any nonlinear trend in the data?
Yeah, it seems not strong.
It's certainly not strong. I mean, or at least from what our residual plot, it doesn't appear to be that strong. We can, I guess that kind of depends on what the Y values are. But as far as it goes, I mean, I don't see anything. You could maybe convince yourself there's something like this going on, but I mean, it's not super strong. So I would say that it probably meets the linear well enough where that's not the main problem with this residual plot. As far as independent and random, those aren't even options down below. So basically, it's either normal or equal variance.
Would it be not normal because it doesn't meet the large counts condition?
Normal for this would be checked with the normal probability plot or the distribution. So as long as your normal probability plot looks like this, you should be fine. Now, honestly, it doesn't give us information on normality, but it doesn't even it doesn't give us that as an option in our answer choices. So just to kind of answer the question, what it appears to be going on is like, and hopefully you can see this, it looks like this is widening out just a bit as we go from left to right. And this would be, at least in some small way, a violation of equal variance. So they don't say this violates equal variance. What they do is they phrase it this way: the variance of the response variable is constant for all values of the explanatory variable. And that is a condition that we should be meeting, but we don't meet it. So that's the one that we don't meet. I'll pause there because I'm not sure if that is completely making sense. So if there's any questions, I'll pause. Okay. If that's something you do want to come back to later, you can make note of it. But let's see what's going on with this. Now we got some fun stuff. We have a printout. It is find the appropriate test statistic. They're comparing number of hours per week spent exercising and the number of seconds it takes to run one lap around a track. All right, and there we go. So keep in mind, the only values here that matter, we don't care about the constant. The only values that matter for t-statistic is going to be the stat. We already know, well, I didn't need to write it that way. Our parameter is going to be 0. And then the standard error. So in our case, it's going to be B over the standard error. And those are given right here. So this is actually a very simple problem. Our slope is negative 2.20. Our standard error is 0.07. And that's our answer. And this is a crazy difference between the slope and the standard error. So if we find, it doesn't ask us to in this problem, but it's just out of curiosity to see what this test statistic actually is. It's negative 31.43. Just how crazy is that? This is something that if people who weren't in a stats class were watching, they'd be like, big deal, it's 31.43. That doesn't mean anything. But you guys know with a test statistic just how crazy that value is. Okay, now the question didn't ask that, but why not? I'm nerdy enough that if that was on a test, I'd be like, wait a second, I just want to calculate that. So anyways, we are now looking, we got just a couple of FRQs. We're actually gonna wrap this up pretty quick today. A couple of FRQs to go through. And the second one we're not even gonna do, we're just gonna kind of look at it real quick. So in this one, I like this one because it reviews some stuff we looked at back in Unit 3. So let's read it real quick. A taxi cab company in a large city charges passengers a flat fee to enter a cab plus an additional fee per mile. There's also a charge for time spent stopped in traffic. The company wants to develop a new method for determining fares based on mileage and a flat fee only, not on time spent stopped in traffic. A random sample of 10 recent cab fares was selected and the distance in miles and the fare in dollars were recorded. A regression model was fit to the data and the output, scatter plot, and residual plot are given below. Now it's interesting that they give us the scatter plot and the residual plot because we really don't need them for this problem. But the reason they give us all this information, just so you guys know, is because we don't know what information we need until we read the questions. So if they only give us what we need, then that makes our job a lot easier. If they give us way more than we need, then we have to kind of look through everything to figure out what's important. So the first thing it asks is, what is the LSRL, the least squares regression line for this data? This goes back to Unit 3. Okay, and we know that the intercept is the first line, and normally I'd cross this thing out, but here we actually need one value. Our regression line is going to be A plus BX, and I need the intercept and the slope. So my intercept is 4.296. And the intercept is 1.229. All right, now this is not a final answer because it asks to define any variables used in the equation. And this is also some review from Unit 3, because what we could do right here is I could say that y hat is the predicted fare, and x is the mileage. And I could put miles just to show the unit and dollars. Now I could do that. I could also do something like this. I could say that instead of y hat, I'm going to put fare hat equals $4.296 plus $1.229 per mile times X miles. All right, so at that point, it's kind of defined. You still might want to add a little bit more explanation to it. Just, you don't want to under explain. You don't want to over explain either, but just a little bit more to explain that. But remember, you could write this equation different ways. And this will hopefully remind you of that from Unit 3. So I wanted to do that part of the problem for this. Now the next part, it says we have a 95% confidence interval for the intercept of the least squares regression line, which is 3.61 to 4.98. But notice, this is a confidence interval on the intercept, which we have not done anything with, but it's already been calculated. So I won't worry about it. The next part says construct a 95% confidence interval for the slope. And we do know that one. So let's go ahead. I'm going to state the problem. I'm estimating or drawing an inference about beta, which is the true slope of the relationship I don't know, between fare and mileage. So that's what I'm predicting. My confidence level is 95%. My plan is to do a linear regression t interval. Now right here, it says assume the conditions for inference are met. So I could say something to that effect. I'm going to put a check mark for right now, but I would maybe want to write a sentence that says conditions for inference have been met according to the problem. This is the heart of the problem. So this is going to be the generic form of stat plus or minus the critical value times the standard error. My stat is B, T star is the critical value here. Now, I would go ahead and even write S over S sub X times the square root of n minus 1, even though I am not given S or S. No, I am given S, but I don't have S sub X. And as we've seen a few times, that doesn't matter because they already give us the standard error right here. We can forget about the intercept at this point. So now I can just substitute in 1.229 plus or minus 0.166. And the T star, well, I've got, let's see, it was 10 recent cab fares. So N equals 10. My degree of freedom is going to be 10 minus 2, so 8. So I'm going to find the critical value for 95% confidence level with 8 degrees of freedom. You guys can look that up. All right. And the number I got was 2.306. And let's go ahead and calculate this, get the actual confidence interval just for completeness sake. All right, so I've got 0.846 to 1.612. All right, so there's the confidence. Of course, we can conclude this. You say we are 95% confident that the interval from 0.846 to 1.612 captures the true slope of the relationship between cab fares and mileage. There we are. I know it's not fun watching me go through the full process, but I do it every time so that you guys have seen it so many times that you're like, you kind of can predict what's coming up next. So I hope that's the case. And hopefully we got the same answers if you guys were doing the calculations at home. And if we didn't, then that's something we can come back to and look at. So I'm going to erase a bit of stuff going on. We can look at the last part right here. And the last part says, the company wants to know if charging a flat fee of $3 and a per mile charge of $1.50 will maintain its current revenue. Based on the information in part B, is a flat fee of $3 a reasonable value? Okay, now this is one in 5th hour. Well, actually, let me just, I don't want to say anything right now. What are your initial thoughts on how you'd approach this question? Okay, so that's a very good answer right here. So if we're looking at this, the interval given for kind of the starting point for their current revenue is between 361 and 498. And when you look at this $3 now, there's a good chance that they're actually going to be losing some of their revenue because they're not charging as much to start off with, while this 150 is in their current confidence interval for their per mile rate. So you could almost think of it as they're going to continue getting the per mile amount the same, but they're losing revenue for what their initial cost is. And that's a tricky one. I'll admit I had to kind of dive into this question a little bit more. And it didn't come to me as quickly as it did for Sam. So it's a tricky question, but it's worth pointing out that this is an interpretation question, no doubt. And that's what these FRQs are really doing. It's not just, hey, can you calculate this? Of course you can. But now interpret this, and we're going to ask you a question that kind of goes beyond just a simple template answer, and interpret this a little bit further. So some of these, if you think of an FRQ taking you 15 minutes, I'd hope that this part would take you about 1 minute. This part, depending on how fast you work, might take you about 5 minutes to do. If you really forgot some stuff and you had to look, that could stretch out to a little longer. This one right here, you might need to spend, 9 or 10 minutes on. Maybe not. Maybe it comes to you really quickly, but that's kind of how you can think about these problems. All right. So let me clear this. And this FRQ right here is available online. It's really nothing special going on with it. It asks you to construct a 95% confidence interval, and then it asks you an interpretation question. And I actually won't go into it at all, but it's available there if you wanted to get some practice with it tonight. So as far as your homework goes, I just want you to work on the problem statement. If you have questions about your project, you can stick around. Work on your Unit 9 progress checks. That's going to help you with the multiple choice, no doubt. And you can finish all the homeworks that you did. That'll help you with the FRQs a little more, but just kind of get a well-rounded understanding. So if you have any questions, stick around. If you're good to go, have a wonderful day, and I will see you tomorrow for your last unit test.